Alright, so I'm going to show a demo of my injector tester test rig right now. I'm going to go ahead and upload the code to show it does in fact compile and work out of the box. Alright, so this is the interface. We need to go ahead and connect to it. Right here is where all of the values will be shown as they're calculated. Over here is just the serial monitor where it's spitting out commands. Here you can set any RPM basically that you wanted to test at. 6,000 RPM seems to be the standard test rate because it makes a direct correlation of duty cycle to pulse width. And then here in the middle I have the time in seconds requested for testing. So we'll go ahead and we'll just use the default for now. So we'll go ahead and hit set RPM. And see now it calculated, it's showing the times requested, calculated frequency is 100 Hertz, simulated engine speed is going to be 6,000 RPM, and output duty cycle and pulse width are both showing 0 because it's not running currently. So I'm going to run this for, we'll go ahead and change this to 10 seconds. We'll hit set timer, and now this is calculated as 10 seconds. Change this to 50% duty cycle, which will equate to a 5 millisecond pulse width, although this could be set to realistically any figure. 47.1 would equal to a 4.71 millicycle pulse width. We'll just go back to a standard 50%. Now this button right here will cause the code to run and actually begin the timing function. So I'll go ahead and click run. Now you can hear the injector going off. The output duty cycle is 50%, pulse width is calculated to 5 milliseconds, and it automatically shuts off. And you can repeat this as many times as you want, just hitting that button. And again, you can change any of these parameters that you want. So if I wanted to do, testing idle characteristics. Sorry, okay. So I changed the RPM and it reset the counter. That's the scenario that I have yet to actually test, so it's good to know that the code doesn't crash. But yeah, it's going to test at 600 RPM, which is equal to 10 Hertz, and it's doing a 50 millisecond pulse width at 50% duty cycle. So here is the little testing board I made. It's got an Arduino Nano, a little pull-down resistor. I added 2 diodes just for protection because I kept blowing this MOSFET out just while I was probing around with the oscilloscope, and I didn't want to fry the microcontroller when this inevitably would short out, so I put in a diode protection for that. It's heat synced right now. The injector at 6,000 RPM or 500 is only simulating, or it's only drawing approximately a half an amp. I haven't done any wide open 100% duty cycle draw tests, but right now I have everything feeding off of my lab bench supply. I don't know if you can really read that, but right now it's set to 14 volts. Oh, something's going on with it right now. Well, the situation that I was just talking about happened. The MOSFET just shorted itself out. So now I gotta replace that. I'm still doing some troubleshooting as far as nailing down a much more robust circuit design. This is just for testing at the moment. But you heard the injector buzzing in the background. I was going to show the waveform on the oscilloscope. I can still do that with the just looking at the output on the the output of the microcontroller itself. Go ahead. Oh, it's too slow at the moment. Let me bump that back up. I don't want to reach over in. So we have a nice square wave going on right there, coming out of the microcontroller, and it times out after the set time. So that was a quick demo of what this system's designed to do currently, so hopefully that gives you a little insight. Okay, update. I was retarded. My leads were shorting out, which was causing a constant current protection. So when I unshorted my leads, now everything works as expected. So 6,000 RPM, the timer set to 10 seconds, and I got 50% duty cycle set. Go ahead and hit run. So here's the setup going. And here's the output on the waveform. I'm still trying to figure out that little dip. I'm pretty sure that's coming from the loading of the coil in the injector itself that's causing the voltage to drop all the way to 0 volts before it starts to recover. But that's something that can be dealt with at a later date, because the concept is that everything works perfectly fine up to this point. But just to show, the duty cycle does change in the oscilloscope. The on time is the top little blurb, the off time is that lower bit. And I can set it all the way up to approximately, I can go all the way to 100%, but the injector stops responding at about 92-ish%. You see, again, at 90% you can see that the on time now is almost all the time. There's not a whole lot of off time. So everything does appear to be working in the software side, and so far the hardware seems to be working. So now it just needs to be made more robust. I'm anticipating putting in an optocoupler to protect the microcontroller, as well as some protection diodes, dropper resistors for current limiting, things of that nature, and then scale it up. I'm still debating if I want to do one MOSFET per injector that I plan on incorporating, or if I want to be able to run multiple injectors off of only a couple of MOSFETs to try and keep costs down. I mean, if I set this to 100%, I don't want to run it for that long, so I'll go like 5 seconds. But if I do this, my current, unshort those leads. My current, I'm only drawing 0.8 amp, and this MOSFET right here is rated for up to 30 amps with optimum cooling. So I think with it being heat sunk, I might be able to run 2 or 3 injectors off of each MOSFET before I start worrying about thermal breakdown. But that's all I have right now.